Welcome to part 3 of lesson 18DE. In this part of the lesson, we are going to just look at more examples of how we can use normal distribution and also binomial distribution to solve problems. So example 7. Given that x belongs to a normal distribution with a mean of 3 and a variance of 16, which means that the standard deviation is the square root of 16 or is 4. And then in part A, we're looking for the probability when x is greater than 5. Hopefully, you have had some practice on this and recognized you need to use the normal CDF on your calculator, inserting 5 as the lower bound, a large number like 1000 as the upper bound, and then mean is 3, standard deviation is 4. The calculator should give you 0.309. Next part, we're going to look for the probability when x is greater than 5. This symbol means and. X is greater than 8. So that means these two sections must overlap because this is and. Well, if I want something that is greater than 5 and greater than 8, it boils down to something that is greater than 8. So you can slightly adjust this normal CDF to start from 8, keep all the numbers the same, and get the answer of 0.106. In part C, we're going to look for the probability that x is greater than 8, given that x is greater than 5. Hopefully, you have also reviewed some of the probability ideas that you learned in last year, because the conditional probability has this relationship with the and. So take the probability that's common between A and B, and then you divide it over the given, the conditional, or the restricted sample space of P of B. Okay, so in this case, if we match up the notations here, the numerator will need you to find the and of x greater than 8, as well as x greater than 5. And the condition is that x must be greater than 5. So you divide it by probability of x greater than 5. We have found these two results in parts A and B, so you just sub in the numbers and come up with the result. Example 8. On a cherry farm in the Niagara region, 5% of the cherries weigh more than 8.5 grams and 7% weigh less than 5.1 grams. If the masses of cherries are assumed to be normally distributed, determine the mean mass and standard deviation of the cherries. So this is very different from what we have been seeing so far. In most of the questions that we have been doing so far, we are given the mean and standard deviation. And then we just answer some probability question, right? Whether it's finding the actual probability given a position that you're sitting on the normal distribution curve, or you reverse looking up the position where you are based on the probability. Same thing. Okay. But this time, we don't have the mean or standard deviation. So in a way, your calculator is not going to be very helpful in that sense, right? And but what we can do is to, take a sketch, look at the sketch, and see what kind of hints we can draw from the sketches. So the first statement tells us that under the same probability distribution, if the cherries weigh more than 8.5 grams, it's going to be only the top 5%. So 8.5 will naturally sit on the right side of the graph, leaving 95% of the cherries weighing less than 8.5 grams. And then the second statement says that cherries with 7% weigh less than 5.1. So with a weight of 5.1, only 7% of the other cherries will weigh less than this. So we're on the left side, okay, on the normal distribution curve. We can translate this into the probability, inequality, whatever you call it, notation, like that. Makes sense. And then with the inverse normal, we're assuming that we're using the most basic inverse normal. Everything must be to the left, the less than equal to type of configuration. So the Z-score corresponding to a weight of 8.5 would ask you to do an inverse normal of 0.95 on the calculator, which gives you 1.64. You can set this equal to the z-score formula, right? You plug in the data point 8.5, subtract the mean unknown, and divide it by standard deviation, which is also unknown. You do the something similar here on the right side here, right? And you come up with another equation that shows you a relationship between the mean and standard deviation. Now, with two equations and two unknowns, we can set them equal to each other and solve for the mean and standard deviation of this bell curve. Okay, continuing. This is going to be the last example. We're going to look at the heights of a group of 3-year-old children. So the heights of these children are normally distributed with a mean of 88 centimeters and a standard deviation of 7.3 centimeters. We're going to look for the probability that a randomly selected child is taller than 100 centimeters. So let's set our variable x to represent the height of these kids. So now x belongs to a normal distribution, mean 88, variance 7.3 squared. This asks us to figure out the normal CDF from a lower bound of 100 to a large number, mean, standard deviation, plug it in, and the probability of having finding a child with a height taller than 100 centimeters is like 5%. Okay? Part B. Now, in a group of 50 children, so now we know the group number, group size, how many are expected to be taller than 100 centimeters? What does that sound like? We're not looking for a particular height here, right? The question here has kind of changed into taller than 100 centimeters versus not taller than or shorter than 100 centimeters. What does that sound like? A binomial distribution. I have the group size, number of trials, 50. We're picking 50 kids. And then the probability of success. Success refers to finding a child who is taller than 100 centimeters. So I can let the variable y to represent the number of children taller than 100 centimeters. So we're looking for the expected value of y in a binomial distribution. The formula is NP, so 50 times that 0.0501 that we got from part A. It's about 2.5 kids, okay, roughly. So 3 kids out of 50 would be taller than 100 centimeters. So part C, in this group of 50 children, find the probability that at least 15 of them are taller than 100 centimeters. So this brings us back to the binomial distribution calculations. Well, then let's write down the notation first. So P of y is at least 15. So at least 15 means 15 or 16 or 17 and so on, right? So anything including 15 and up. So P of y greater than or equal to 15. So remember, on your calculator, binom does not calculate greater than. Everything is less than. So we need to look for the complement, which is 1 minus P of y less than 15. Also note that this is different from the bell curve, because bell curve talks about continuous data. You can have decimals, but binomial deals with discrete data. So if it helps you, draw a number line, right? We keep 15, 16, 17, but now we're removing cases including 14 and down. So when you calculate the probability of y less than 15, when you enter the numbers into your calculator using binom CDF, make sure the number that you put in is a 14, right? That's your maximum case. And then you'll get about 0.999 ... And then subtract that from 1. The probability of finding at least 15 of them, these children being taller than 100 centimeters, will be very small. Okay, it's like 1.32 times 10 to the negative 8. It's like almost 0%. Okay. So hopefully these 3 examples will expose you to, more practice, more variety of problems involving different kinds of probability distributions, especially the last one where we transition from getting the results from a normal distribution and then applying the results to a different model, which is quite common on the IB exam. Okay, so here are the homework for this part of the lesson, and this concludes the entire SL course.